Alright, so in this lesson we're going to look at some graphs of motion and look at how we can use a graph of distance versus time, velocity versus time, and acceleration versus time to kind of talk about what the motion of an object looks like. So the top of these three graphs I've graphed distance or displacement versus time. In the middle of these I have velocity versus time, and in the bottom of these I have acceleration versus time. And there are a number of different things in here that are indicators of certain points of these two graphs. If we look at distance versus time, this very first region, what happens is it starts out at a distance of 0, the distance increases, and the slope of this line increases as we go from this point to this point. Now, looking at the slope of this line is important because velocity is ultimately the slope of a position versus time graph. So here I have a position versus time graph. So the slope of this line is going to be equal to what the velocity is. So if the slope is increasing, that means the velocity has to be increasing. It's also worth pointing out the slope is positive in here, which means that the velocity is also positive. So here we have a positive increasing velocity. That's what this looks like. Now here we have a positive slope. It looks like a constant slope. And the thing to remember about the relationship between acceleration and velocity is that acceleration is ultimately the slope between a velocity on a velocity versus time graph. So here, if the velocity is increasing, that means we have a positive acceleration. We have a straight line, so that rate of acceleration or that slope is constant, and so my acceleration is constant. Go to the second region, it looks like distance is still increasing, but it's increasing in a way that we have a straight line, constant slope. What constant slope means is constant velocity. Well, here the slope of velocity is 0 for this region, and so that means the acceleration is 0 in that region. Now if we go in this whole region in here, and let's go up just to 15 here, and what looks like is happening is that the distance is still increasing, but the slope of the line from here to here gets smaller and smaller, which means that the velocity is decreasing, but is still positive from this dashed line up to the highest point, this 15. So what we have is a positive slope and still increasing, or excuse me, decreasing until we get to that top point. At that top point, if we were to draw the slope of the distance versus time graph, I would have a slope of 0 at the very top point. Now what that tells me is the velocity is 0. Now the velocity is constantly changing through here. It's always negative all the way down to here. It's also negative all the way down to here. Looks like this is all a straight line from really about 7 seconds to about 23 seconds. And so what this tells me is I have a negative acceleration that's constant. So at this point 15, we have a positive distance, a 0 velocity, and a negative acceleration. Just because displacement is positive doesn't mean that velocity or acceleration need to be positive. Now if we look at from this point at 15 seconds down to the next dashed line, we have a slope that's increasing and it's becoming more and more negative. What that would indicate is that we have a negative velocity that's becoming larger and larger in the negative direction. We already talked about this region for velocity and acceleration, that basically from this dashed line to this dashed line, the velocity versus time graph has a constant negative slope, which means has a constant negative acceleration. So really from here all the way up to here, all the way down to here, this looks very similar to what free fall would look like if we throw a ball straight up in the air, measure its distance that has traveled up as a function of time, its velocity is a function of time, and its acceleration is a function of time. Now when I get to here, go from there to the next dashed line, the slope is still negative, but it's getting closer and closer to 0, becoming less negative. If I wanted to draw that in terms of velocity, we'd start here, become less and less negative, get there. On the velocity versus time graph, we have a positive slope that's constant, so I have a positive acceleration. In the last little region, we have a distance versus time graph which is flat. 0 slope indicates 0 velocity, object is at rest. In this case, since it's a constant 0 velocity, acceleration is also 0. Now it's worth pointing out that you could work backwards in these as well and calculate out what distance versus time looks like from velocity and acceleration. If we were to take the area under this curve at any point, say up at 15 seconds, calculate this whole area, what that would really tell you is what is this maximum distance you've traveled up here. Same thing you could do up here, calculate this whole area, you could calculate the velocity at 15 seconds. So there are lots of little relationships in here with slope and areas that relate distance versus time, velocity versus time, and acceleration versus time. Ultimately, this problem here is the basis for differential calculus. What I explained to you in this short lesson is, I would say, the conceptual idea behind probably the first semester or semester and a half of calculus that you would study. So looking at a graph of motion, what you should be able to do from a distance versus time graph is tell me where are areas where the velocity is positive, where are areas where the velocity is zero, where are areas that the object is at rest, where the acceleration is positive, negative, or zero. Those are all things that you should be able to do just by looking at one of these graphs.